Welcome to qnawire.
Okay, let's look at these groups. We've got carbon, doubly bound. Oh, I don't like the way these are drawn, sorry. Okay, so we've got to consider whether this is donating or accepting through resonance or inductance, right? So for inductive effect, I just like to consider whether this is going to be partially positive or partially negative, roughly, through viewing in any relevant resonance forms or bond polarization, right? So one relevant resonance form might be this, for example. Right? There's no real resonance form that'll put a positive charge on this carbon. If anything, the resonance puts a negative charge on this carbon. So in that way, inductively, it's donating, right? So we're really just looking at charge. Okay. Now we've got to consider whether via resonance it is an acceptor or a donor. So this seems like a similar thing, but it's actually like different. So recall that this has got a pi bond here, and recall that there's a resonance form where we can draw donation here to get the following, which would create a pi bond here. The point being that in actual fact, this system is something like this, and this is a pi system with electrons in it, and that this pi system is going to be overlapping the pi system that we have in the benzene ring. And so this is going to be donating through resonance. So, and really, in either case, this is donating. Okay, now let's move on to this other group. All right. So inductive and resonance. Let's start with inductive. Is there some partial charge on this carbon? We can consider what the formal charge would be for its most relevant resonance form. Which would be negative, right? So there is some partial negative character to that carbon. For that reason, this carbon is going to be inductively donating. Okay, now let's consider the effect through resonance, and it's basically the same exact picture that we got from the previous molecule. There's a pi system between these three molecules, even if it might only look like it's between these two. But when we consider that this nitrogen could donate its lone pair, clearly this into that pi system, we know basically just like in an amide, right? We know this is actually planar. Even if this nitrogen looks like it's sp3 hybridized, it's actually sp2 hybridized because there's overlap in this pi system that this lone pair participates in. Same idea here. This is going to be planar all across, and this pi system is going to be capable of donating electrons into the benzene ring. All right, finally, we have CH2OH. Okay, this. All right, so consider the inductive effect. Well, we know with carbonyls that the major resonance form is one in which the lone pair goes up onto the oxygen, giving us a positively charged carbon and a negatively charged oxygen, which means that this carbon is typically partially positive. And to some extent, this oxygen will be pulling electron density through the sigma bonds as well, making this very slightly more partially positive than it would be otherwise. So through the inductive effect, we expect this to be withdrawn. Now we can consider resonance, and here we've got the same idea before, where we've got a pi system here, but in this case, this is essentially each of these has one electron, but the oxygen is pulling so much more strongly on this that, and also consider that when we draw the resonance structure, we've got this positive charge here, indicating that the balance of electrons is much more heavily favored for oxygen. Like we can also consider that if we wanted to look at the effect that this would have in the ring, if we were to draw a resonance structure, right, we could show this and then this. If we take that resonance into the ring, it's going to be one that puts a positive charge in the ring and not a negative charge like we might see for if we took, as a counterpoint to that, the resonance form for this would involve donation there, creation of a double bond, and then pushing a double bond onto a single carbon, which would introduce a negative charge into the ring, right? So this is why the carbonyl group is withdrawing through resonance, whereas the sort of conjugated double bond with a neighboring oxygen with this lone pair available is donating through resonance. We could also consider that there's another sign is that there's a free lone pair, either neighboring the ring or neighboring something conjugated to the ring. There's no free lone pair in this carbonyl when it's in the carbon that's neighboring the ring, right? So we're either looking for a lone pair, like the difference. How can I put this? If we've got our ring here, if this atom with the X on it has a lone pair, or it's in a conjugated system, and this atom has a lone pair, then it's going to be donating through resonance, right? If instead we've got this sort of system and there's no lone pair there, or there's a conjugated system, but there's is like in the case of the oxygen, it's true that it has a lone pair, but it's not in this position or this position. Just put like an A there. A lone pair here won't help, right? So we need a lone pair neighboring the ring or neighboring the conjugated bond that's conjugated to the ring to be donating through resonance.